In this video, we're going to talk about the third and arguably the most important trend on the periodic table. In fact, this concept is so important that it might actually be the single most important concept in all of Chemistry 11 because of how fundamental it is in explaining the behavior of different elements. And that concept is electronegativity, which very simply is a measurement or a quantification, because electronegativity actually has a number associated with it of how easily an element is able to gain electrons from other elements and how easily an element is able to hold onto its own electrons and prevent other elements from being able to take them. Not surprisingly, because metals, which make up the left side of the periodic table, have a very low electronegativity, while nonmetals, conversely, tend to have a very high electronegativity. And in this video, we're going to explain all of the justifications based on atomic radius, ionization energy, and the number of valence electrons in order to justify why this is. Now, with this periodic table where we can actually see the electronegativity values for all of the elements, which very simply are what we call electronegativity constants, because these are actually measured values that generally do not change as long as we were on Earth. In fact, on your periodic table, you should be able to find the element's electronegativity constant right below the atomic number. So, for example, iron's electronegativity is 1.8. So, there's no ambiguity about how electronegativity changes when we go up and down or left and right on the periodic table. So we can clearly see that as we go upward from bottom to top on the periodic table, our electronegativity increases, and we can justify this by comparing the atomic radius of two different elements. So let's look at hydrogen, which is the smallest element on the far left of the periodic table. We know that hydrogen only has one shell with one electron right there. And we're going to compare this not to lithium but to sodium for an even more obvious comparison, because sodium has a full first shell, and it also has a full second shell with 8 electrons, which I'm just writing in here, and you actually have to go to the third shell before we get to sodium's valence electrons. So obviously hydrogen has a much smaller atomic radius than sodium's, because sodium you actually need to go to the third shell in order to find its valence electrons, and obviously this shows that atomic radius increases downward. It increases from top to bottom, meaning that valence electrons are farther from the nucleus as you get lower and lower and lower and lower. And as we talked about with ionization energy, the farther away valence electrons are from the nucleus, which is where all of the positive charge in the element is, the weaker the attraction is between the nucleus and the valence electrons. And as this attraction becomes weaker, that means that you need less energy in order for this element to lose its electron. Now, an element that has a very, very low ionization energy means that it must have a very, very low electronegativity, meaning that because of how far away the valence electrons are from the positive charge in the nucleus, the easier they are to remove and the less good the element is at holding onto its own electrons. And this makes perfect sense. Metals do not want to gain electrons in order to gain a full outer shell. They prefer to lose electrons, and that's why electronegativity increases as we go from bottom to top along the periodic table. Conversely, when we read the periodic table side to side, we can see that electronegativity clearly increases as we move from left to right. And there are a number of explanations as to why this is true. And firstly, we can use the same justification as atomic radius by looking at the number of protons. And as we move from, say, lithium all the way up to neon, the number of protons increases, obviously, because that's how the periodic table is organized. Lithium has 3, beryllium has 4, boron 5, carbon 6, nitrogen 7, oxygen 8, fluorine 9, and neon 10 protons. So this means as the number of protons increases, the number or the amount of positive charge increases. So as the amount of positive charge increases, this means that an element's valence electrons are going to be pulled closer to its nucleus, which is why sodium has the largest atomic radius in its entire period, because it has the fewest protons and therefore the least ability to pull its valence electrons closer to the nucleus because of the attraction. And as valence electrons are pulled closer to the nucleus, this makes them harder to remove because the attraction between the nucleus and the valence electrons gets stronger. And if valence electrons are harder to remove, this corresponds with a higher electronegativity. But actually, the most obvious justifications is by simply looking at the number of valence electrons. So if we count the number of valence electrons just in the nonmetals, boron has 3, carbon has 4, nitrogen has 5, oxygen has 6, and fluorine has 7. So as the number of valence electrons increases within an element, the valence shell gets closer to being full, with the extreme case being fluorine, in that it is only 1 electron away from having a full valence shell. This probably means that fluorine is much, much better at gaining electrons than losing electrons, not only because its valence shell is very close to the nucleus, but also it only needs 1 electron in order to have a complete octet, or a complete outer shell. And if a valence shell becomes very close to being full, therefore, that makes them much harder to remove. So once again, once you understand the relationship between atomic radius, ionization energy, and the characteristics of the atom, electronegativity becomes relatively straightforward to justify. And in the next video, we are going to look at how electronegativity can be used in order to characterize the way that elements form bonds with one another. So until then, see if you can use your knowledge of electronegativity in order to answer the practice problems below.